Isn't this not diagonally dominant?
This is actually not strictly diagonally dominant. That's a good question. Is this diagonally dominant? It is not. So let's go to the page where we discussed why it has to converge for diagonally dominant system. So diagonally dominant means the diagonal has an absolute value strictly greater than the sum. For our matrix, our diagonal term has an absolute value of 2 over delta x squared, right? That's the absolute value. The off diagonals have one or two terms. It's one term only for 2 points. Most of the interior grid points has two terms. The sum of these is 1 over delta x squared plus 1 over delta x squared. They are equal, right? There is no strictly greater. Now when you look into this convergence analysis, that means instead of, if I have equal, instead of this strictly less than sign, I actually have a less or equal sign. That means mathematically there is no way I can prove that the maximum actually decrease every step. I can prove that it wouldn't diverge, the error would never actually increase, but I can't really show it'll decrease either. That's what happens for equations that has a greater or equal sign in the diagonal dominance as opposed to strictly greater sign. Empirically, the more terms you have that are strictly greater, right? So usually the Jacobi still converges unless all the terms are equal. I mean, if all the terms are equal, there is actually no way you can. It still may converge, but like it's harder. But like if you have more terms that are strictly greater, the more chances you have for faster convergence. For Poisson's equation in 1D, that's actually the worst case, because you only have two terms that are strictly greater, the two boundary terms. All the other terms are strictly equal. If you go to 2D and 3D, the situation is actually better, because for all the boundary terms that are not Newman boundary conditions, you have strictly greater. All right. And this also gives a little bit of intuition of why when I increase or decrease the grid point, the convergence would change. So, for example, if I want to increase n to 200, what do you think? It'll converge slower. Yes, because previously I have 98 strictly equals and 2 strictly greaters. Now I have 128 strictly equals, right? Okay, so we can do the same thing. Let's see, we compute the dx again, and I compute the b again. I compute the x equal to zeros again, and x 0 again. And now let's start by doing these many iterations. And let's clear the figure, not clear all, but wait. I already plotted the solution. I already plotted the solution after these many iterations. So let's evaluate again. Right, so we can see that even after 10,000 iterations versus 20,000 iterations, the solutions still are changing, right? And if we do this again, it is still changing between 20,000 and 30,000, and then it's changing a little bit slower and even slower. Now it's pretty much we can claim it's probably converged, right? So this is after like 10, 20, 30, 40, 50,000 iterations. Convergence got much slower after increased by a factor of 2 the number of grid points.